And I apologize, my bandwidth doesn't allow me to share my video right now, but still I wish you all a good morning, afternoon, evening, or night as the case may be. Wanted to thank the organizers for the opportunity to participate in this workshop. And one of the things I really appreciated about it is the way it's bringing together such different communities, and especially this combination of the exoplanet community and the solar system community. So I will be talking about exoplanet aurora with the starting point of Mars. And what you're seeing on the screen here is actually 3 different forms of aurora on Mars, some of which are probably not known to all the members of this workshop. And that'll be why I'm using as a case study for exoplanet aurora. So learning from the solar system has been one of the themes, and another theme is that when you ask a simple question, the answer usually comes back, it depends. And so I'm going to talk about how the lesson of Mars suggests to us that it may be risky to too quickly attribute auroral emissions to magnetic field activities. Okay, so let me go forward because it really hinges on a clear definition of aurora. And my working definition is really about physics and not semantics, but in general, it's any form of electromagnetic radiation that's caused by precipitation of energetic charged particles. And what's most familiar to people are the visible ultraviolet, X-ray, or infrared emissions that are caused directly by the precipitating particles colliding with the background atmosphere of the planet. I really make a distinction here about radio emission that's caused by the acceleration of particles in the planetary magnetosphere, and this can be up to several planetary radii away. And so this really is a different physical process. They're often lumped together because starting with the terrestrial example, they all sort of happen simultaneously, but the lesson of Mars is that they don't. So in fact, a lot of what we assume about planetary aurora starts from the terrestrial experience, and this idea that with our auroral ovals, we're seeing the precipitation caused at the edge of planetary dipole fields, and that influences our thinking when we start considering other planets. I'm just going to bring up this article, really nice piece of work about the importance of auroral emission over incredible size range. And I only draw attention to the first sentence that you see there, because one of the things we've learned from Mars is that aurora are also detected from non-magnetized planets. And so this opening statement, I think, needs to be broadened. And this is one of the reasons why I submitted this abstract. The other thing that I want to do is sort of to nip in its infancy a potential misconception that aurora are an indication of habitability. This is a very moving essay that I found online, and it really talks about appreciating the view of the aurora and connecting it to the magnetic field, and the magnetic field protecting the atmosphere and therefore being necessary for life. And while these are wonderful perspectives to have, we as scientists have to be careful about connecting all these dots. And I'm going to show you some cases where our best guesses have not been correct. So Mars, I think, is a really valuable lesson for exoplanets because as a small terrestrial planet, it may be typical of a significant class of exoplanets. We've already heard about its unmagnetized or weakly magnetized, and Yashua talked about the crustal magnetic fields, which are the only measurable fields there now. But the other lesson we're getting is that the MAVEN mission has discovered types of aurora that challenge those preconceptions. I'll start with what's already been alluded to, which is these crustal fields shown in a map on the left-hand side, and an artist's conception on the right-hand side that's indicating the patchy aurora that corresponds to the cusp regions between those closed magnetic field regions. And this, if anything, reinforces the terrestrial idea that aurora are restricted to the edges of magnetic fields. The MAVEN mission has actually imaged these. We don't need an artist's conception anymore, although this is a very, if you can follow my cursor there, these wisps and tendrils are real emission. This emission is caused by particle acceleration in the Mars magnetosphere and are an important tracer of the interaction with the solar wind. So when you hear the words charged particle acceleration, you'll recall that that's what gives rise to radio emissions. It could happen here, but due to the weak fields, they change the wavelength of the emission and they also change the strength, possibly too faint, but let's not restrict our thinking when we expand to exoplanets. So space weather does something different to the planet. These are ultraviolet images of the Mars atmosphere, the Mars night side specifically, during the 2017 space weather event, which gave rise to aurora that spanned the entire night side. This is global aurora, made possible, of course, by the lack of a global magnetic field. This is an image from the height of that space weather event. And even though solar activity was low, we saw very bright emission at the limb and on the disk of the planet. And it actually penetrated down at least to 70 kilometers at the energy range of interest to us. But more to the point, the aurora here, both ultraviolet and certainly in the visible, could have been visible to astronauts, but it would be hazardous. So when Elon Musk or whoever makes it to Mars, won't be writing eloquent poetry about the aurora there or its indication of the planet's habitability. At the time of this image, the RAD instrument on the Curiosity rover was measuring harmful radiation. So not an indication of habitability, but in this case, aurora are indicating potential DNA damage. So that's a second type of aurora that MAVEN has observed. The third kind occurs on the day side, and this is caused by the penetration of solar wind protons into the upper atmosphere, charge exchanging with the corona and giving rise to Lyman alpha glow. Not necessarily a particularly bright form, but it actually is the most common form of aurora. And we've learned on MAVEN that it's actually a tracer of atmospheric escape. The proton aurora is bright when the hydrogen corona is expanded. So this has been observed very frequently, and it's likely to occur on Venus, although the right instrumentation hasn't been there to measure it. And unmagnetized exoplanets with hydrogen exospheres likely also have this. I should have mentioned, by the way, when I talked about the global aurora seen on Mars, that's also very likely to happen on Venus. There have been ultraviolet measurements that indicated that from Pioneer Venus orbiter. And I hope the future Venus missions will be able to make those measurements as well. So 3 types of aurora from 3 different causes. And what's remarkable about these is that 2 of them are possible due to the lack of a global magnetic field, and neither one was predicted ahead of time. I guess to be fair, proton aurora was predicted, but the word didn't get through the community adequately ahead of time. And so I think that shows the value of a workshop like this where we can make these connections in a timely fashion. So summarizing just the nature of these auroras is that the lack of the magnetic field has enabled new forms of aurora, and so global magnetic fields need to be considered either the cause or prevention of different types of aurora. So implications for the solar system and exoplanets, it suggests that if you have small exoplanets that don't have magnetic fields, that they are actually likely to have aurora induced by solar or stellar activity, where the acceleration happens at the star and not in the planetary magnetosphere. And the fact that these emissions are global instead of confined to a narrow auroral oval near the poles might mean that the brightness of these turns out to be comparable in a planet integrated sense. And so
2 minutes.
Good. That's just what I need. So the atmospheric emissions are caused by the actual particle precipitation, but you need acceleration at the planet to give the radio emission. So I think I'm the third or fourth person to refer to these observations of radio emission, and I think it's quite relevant that and timely for this conference for these observations to look so promising. There's been no measurement of radio emission from auroral activity on Mars, and so I don't think we really know how to scale up what's happening there. So let me end with conclusions and some cautions and a provoking question towards the end. So aurora in the atmosphere's unmagnetized planets are fully expected, and that's because there's nothing to protect them from the precipitation of energetic solar or stellar particles. And in fact, our first reaction on seeing this at Mars was a bit of a dope slap, saying, why didn't we think this was going to happen? Nothing can stop those particles from causing aurora. And so that means that optical, ultraviolet, infrared, and X-ray emissions are not good discriminators for planetary magnetic fields. And when UV scope or even better telescopes are invented, you have to be careful about interpreting those emissions from a planet as evidence for a magnetic field. And a real warning to all of us is that if we had been capable, if the technology had existed for unresolved ultraviolet imaging of Mars before the MAVEN type observations, we probably would have reached the wrong conclusion about its magnetic field. And I want us to be careful going forward with exoplanets. I think it's much more robust to use radio emissions as a discriminator of global magnetic fields. But the caution that I would like to give here and the provoking question to the community as a whole, have we thought enough about false positives, about unexpected magnetospheres that might also give rise to radio emissions? And I think once we've done due diligence there, we can go forward with greater confidence on the interpretation of the radio emissions. That's all I have to say. Thanks for your attention.
Thank you, Nick. We see comments from Bob Strangeway in the chat box. A couple of comments on where aurora occur. At the Earth, the night side aurora are on closed field lines. At Jupiter, most of the aurora are also on closed field lines. Do you want to comment on that?
I'd have to say that I don't think that affects the interpretation of the 2 points that I'm trying to make are that ultraviolet emission doesn't require any field lines. And Bob, I'm not sure if I'm really capturing the point of your comment here.
If I can comment, it's just on one of your slides, you said that the aurora were near the closed field lines, and I just wanted to address that because it goes to the radio emission source, that you need to be on closed field lines to get the radio emissions, basically.
Good, thank you.
Thank you, Bob, for explaining. We have a second question from Chuanfei Dong. Nick, can you remind me if people have observed aurora at Venus that is similar to what we observed at Mars? The paper you referred to may also include weakly magnetized cases like Mars in general.
Yes, and I also saw in the chat window a reference to Pioneer Venus where ultraviolet emissions were detected. Didn't have the capability for planet-wide emission, but it's fully expected that on Venus, the aurora would have been global. This has also been detected in ground-based emission from the oxygen emission lines. In a very elegant experiment, we get to see the Venus night side. And so even those measurements detected auroral emission from Venus.
Cool, thank you very much for answering that. And yeah, that would be all the talks we have today. And I believe we still have a couple of more minutes, so we can, if people have more questions, please feel free to just unmute yourself and ask, or we can have some discussion on the big questions like what is the near-term future work we'll need to do to answer the very big question for our workshop, like the influence of the global magnetic field on ion and atmospheric loss in the planetary habitability, or maybe our speakers will like to share their point of view on what is the #1 unresolved questions in your area. So yeah, everyone, please feel free to unmute yourself and share your opinions. Tranvi, please go ahead.
Yeah, Nick, actually, I also want to ask a more broad question. How can we distinguish between aurora and night glow, for example, on mankind's planet? Is there any different line? What's the difference? How can we distinguish that?
Yeah, that distinction is fairly easy to make by the identification of the spectrum. And on Mars, we see night glow, which is also called chemiluminescence from a chemical reaction that is responsible for making nitric oxide night glow. But the emissions that we see as aurora require more energetic stimulation than that, tends to hundreds to kilo electron volts. And so it actually looks a lot like the day side.
So there's no overlap between these two mechanisms for the light emission?
I'm going to take my own caution and say what we've seen at Mars hasn't identified any overlap. I think we should be very careful before making that assumption on exoplanets.
Can we distinguish the point source of these two mechanisms, unlike Mars, where we have more, spatial resolution?
Oh, absolutely. And so they also occur at different altitudes in Mars. One is in the night glow, requires a very collisional environment, and the aurora, the precipitation generally stops at higher altitudes, not with the relativistic particles. So there can be some confusion there.
Is there any further questions from audience, or is there any speakers who'd like to share their opinions on like the biggest or the #1 unresolved questions in your field?
This is Nick again. I will try to provoke people by saying, can anybody make radio emissions without a global magnetic field? Anybody know how to do that yet?
Not emissions are like Jovian decametric or terrestrial kilometric, because those are scaling by the global magnet. The frequency that they're generated at is determined by the global magnetic field. It's a measure of that.
Alfred Cohen, I see your hands up. Feel free to unmute yourself.
Well, I can just comment that some people that are participating in this meeting and actually speaking now have suggested that instead of looking for the planet as a source of the radio field, maybe you can look at the background radio emission from the star and look for the modulations of that by the planet. And the planetary magnetosphere, which is, if there is a magnetic field, should be significantly bigger than just the planet itself, even with an induced magnetosphere. So even without the magnetic field, the induced magnetosphere should be larger than the actual planet. So the idea is that maybe it would be easier to detect the field this way instead of looking for a radio source, or to look for the planet as a radio source. Instead, we're just looking at the planet as a disruptor, temporal disruptor of the background stellar field or stellar radio emissions.